Hello guys, you are welcome to this edition of Linear Momentum. And as you listen, God bless you. Now, what is linear momentum? When we talk about the definition of momentum, momentum is a product of mass times velocity. The product of mass times velocity. That means P is equal to what? mv. Product of mass times velocity. And that means that it is measured in kilogram meter per second. That means the unit is what? Kilogram meter per second. Why? Because the mass is measured in kilogram and the velocity is measured in meter per second. So therefore, the unit of momentum is what? Kilogram meter per second. Now, knowing fully well that if you don't know, momentum is a vector quantity. Why? Because mass is a scalar. Then when you multiply it with a vector, a scalar multiplied by vector will give us a vector. So in this case, the momentum is a vector quantity. Now, I haven't defined it that momentum is what? Is a what? Quantity that has magnitude and direction. Now, let us now look at momentum in what? In different dimensions. We have what they call the change in momentum. What is change in momentum? Is just what? mv minus mu. This is what we call the change in momentum. This is final momentum minus initial momentum. This one is called the change in what? Momentum. So if you agree that that is a change in momentum, which is final momentum, mv minus initial momentum. And let us look at momentum as a vector, because we say it's a vector quantity. Now let's look at a case where this is a body, let's say a body of mass m1 moving with a velocity u1. Now let's look at the momentum m2, that means mass m2 moving with a velocity u2 in the same direction. Now what will happen is that when they are moving in the same direction, because we are looking at momentum as a vector quantity. Vector says that when two vectors are moving in the same direction, vector rule, that you add them together. So the total momentum will now be what? m1 u1 plus what? m2 u2, because they are moving in what? In the same direction. Now let us look at a case where one is moving in opposite direction, it's u1. The other one is moving what? m2 is moving in opposite direction with u2. So this is what? Moving in what? This is same what? Direction. This is what? Opposite what? Direction. Opposite. So if you are looking at opposite direction, what will be the what? The momentum. Let's assume that m2 has a higher momentum than m1. So that means magnitude rather has a higher momentum in magnitude than m1 u1. So we are going to have m2 u2 minus what? m1 u1. I'm using u now. We can decide to use v. It does not matter. So this will be the what? A case if they are moving in opposite direction. Now, if maybe probably one what mass is approaching m1, let's say m1 is approaching the equilibrium position, and m2 is also what? Let's call this one mx. Let me call this one my along the vertical. Then this one is coming with the velocity vy. This one is approaching the origin with what? With vx. Now, don't forget that this one will not continue the motion like that. This one will continue like this. Now, if we want to calculate, that means in this case now, the masses or the momentum are perpendicular. So the momentum in this case are what? Are perpendicular. perpendicular. That means at right angle, as the case may be. So if you want to now what? Find the resultant. What we are looking for here is what we call the resultant momentum. Resultant momentum, or what we call the net momentum, is the resultant momentum. What will be the resultant momentum when they are what? Moving in opposite direction. This one, the same direction, this. So, but what they're moving in what? In a way that they are perpendicular to each other. We now use Pythagoras theorem. Now, if you look at the momentum here, will now be what? Let's say Py. The momentum along this is what? Px. Along this direction is Py. Now, how do we find the what? The total momentum or the net momentum square is equal to what? Px square plus what? Py square. So that will give us the total momentum in this case now, because they are at right angle. Now, what I want to do now is this. Let's find the what? The P. P will now be square root of what? Px square plus Py square. So in this case now, don't forget, Px is what? Momentum along the horizontal, which is mx times Vx. Why what? Py is momentum along the vertical, which is my Vy. So this is what? The case 3 of resultant you are going to have to find the resultant when they are at right angle. Now, these are cases of when two masses are moving in opposite direction, the same direction at right angle. Now, I haven't explained this now. What we have talked about resolution, and let us look at a single force. Let's look at the single force, the net force. Now, before we look at the net force of a single object, let us define what? Newton's law, first law of motion. Newton's first law. Let me write it here. Newton what? Newton's first law. First law. Now, what is Newton's first law saying? It says that a body will remain at rest or moves along a straight line with a uniform velocity unless it is acted upon by an external force. In other words, we can restate it like this, that a single object has a momentum that is constant provided the motion is uniform. So that means that the momentum of a single object is constant provided what? The motion is what? Is uniform. So that means it states that what? States that a body what? Will continue in its state of rest unless it's what? Unless it is acted or it is being acted upon by an external force. Now, I told you that this statement can be restated, or this law, this Newton's law, is also called the law of what? Law of inertia. Law of inertia. Because inertia, what is inertia? Inertia is the tendency of the body to what? That is of motion to stop moving, or the tendency of the body that stop moving to continue in motion. Now, to start moving. Now, what we are saying is that you can restate this particular Newton's first law in terms of momentum and say is that what? That the momentum of a single object will remain constant or uniform for a uniform motion of the object. So that can be in definition of what? Of Newton's what? First law. Newton's second law says that what? That the force applied is directly proportional to the what? the rate of change of what? Of linear momentum and tends to act in the direction of the force. So in this case, now the net force is equal to what? F. Now, if you remove the proportionality, then we would have F equal to K mv minus mu over T. But because our mass is already constant, K will be equal to 1. So K will not be valid. The constant of proportionality will be taken as 1, which will now be what? F equal to what? mv minus mu over T. Now, this is what? A net force. So the rate of momentum, the rate of change of momentum is also known as what? Force or net force. Now, don't forget, if you cross multiply, what we are going to have is what? Ft is equal to what? mv minus mu. That means Ft, force times time, is equal to what? Impulse. So force times time is equal to what? Impulse. I just need to check the mic whether it's working effectively. Now, since the what? The momentum is, for changing momentum, is equal to impulse. Now, don't forget that in this case, now, if we assume that the body is starting from rest, once the body is starting from rest now, it will what? U will be equal to what? 0. So if the body is starting from rest now, U will be equal to what? 0. A body starts from rest when U equal to 0. And if U equal to 0, that Ft is equal to mv, because this one will now cancel out. This one will cancel out, or this one will be removed. So this is what? Impulse. Impulse is equal to this. Impulse is equal to what? Momentum. Now don't forget that what? Impulse has a unit of Newton seconds, which is equivalent to kg meter per second. So the equivalent unit of Newton seconds is kg meter per second. So therefore, we can say that the unit of momentum is equal to kg meter per second, as the case may be. Now, in this case now, we have been able to what? Analyze what? The first law and second law. This is what we call the Newton what? Second law. Newton's what? Second law. Now, let me illustrate a case of what? Of this law. For example, if I have two what? Objects, a stone and a feather. Now, let's assume that this stone and a feather is to be thrown at you, to eat you. Now, the question can say, why will the what? The girl, the little girl, prefer the feather instead of the stone? Why will the little girl prefer the feather instead of the stone? So this little girl can prefer the feather because the feather applies a higher what? A lesser force and more time. So that means that the force applied on the boy or on the little girl is lesser than what? And has more time. Because we know that the more time and what? Lesser force will give us the same thing as more force and short time for a particular body with the same mass. Now, in this case now, that means that they hit the boy with the same mass and the same velocity, but the force and the time changes. So if I'm to answer the question, I will say the little girl preferred the feather because the feather applies less force and what? More time. Don't forget the hazard that force can do on the body. It can cause deformation on the body. So that is one of the danger why the girl will not prefer the what? The stone. Number two is that what? The force can cause change of state of the body, can move a body from one position to another. Change of position of a body. Now, that is what force can. We have other things that force can cause acceleration, can cause a body to accelerate. Now, we are going to talk about that under force later in this channel. Now, let's continue. Now, we have talked about what? The application of Newton's first law or Newton's second law. What about Newton's first law? Now, why do we what? Why would the body remain at rest? Now, naturally, a body cannot remain at rest except an external force is not applied to it. So when a body remains at rest, it is because there is no external force that is applicable to the body. Once an external force applied to the body, it will move the body from one point to another. It will change the state of the body. That is just natural. Now, but let us look at Newton's third law. Now, Newton's third law is an application to what? The law of conservation of momentum. Newton's third law is what? An application to the, I'm here now, I'm explaining what? I've explained all the work. I want to explain third law, then I will enter this conservation of what? Momentum. Now, Newton's third law is an application of what? Of law of conservation of what? Linear momentum. What is it saying? Newton's third law says for every action, there is equal and opposite what? Reaction. Newton's third law says for every action, there is equal and opposite what? Reaction. So what it's saying is that what? That F is equal to what? Minus F. If you eat a dog with maybe a stick, you expect the dog to react. It is going to be a kind of strange cases when you eat, or a strange case when you eat a dog and it start looking at you. It's very funny because the dog will react. I hit a dog hard, and as I hit the dog hard, I notice that the dog is not reacting. I'll be so concerned at the owner of the dog that why is the dog not reacting to the action that I've been given to the dog? So for every action, naturally, there must be what? A reaction. So action and reaction are equal and opposite. That is what Newton's third law is saying. For every action, there is always a reaction. And this action and reaction are equal and opposite. So leave it like this first. So now, if this one holds for Newton's third law, what means is that mv minus what? Mu, which is from the formula for force, over time is equal to, let's call this one M1, V1, let's call this one M2, M1, U1. Then let's call minus what? M2, V2 final, minus M1, M2, sorry, U2. Then over time. So that means this one is what? Let's say for force 1 and this for force 2. Now, they have what? Minus, and they are equal in magnitude but opposite in direction. That's why the minus sign is there. Now, since it's a system that occur at the same time, so T1 is equal to T2. They will cancel out. So what will happen is that M1, V1 minus M2, M1, U1, pardon, we would have minus what? M2, V2 minus M2, U2. So in this case now, if you play with it, you would have what? M1, V1. Let's call it like that, or let us open the bracket. M1, U1 equal to, that may change momentum for the first body. Okay, this one is minus M2, V2. Minus and minus is for plus M2, U2. Now, if you collect like terms, let U go to the other side and let V go to the other side. Let's bring this one. You are what about M1, V1 plus what? M2, V2 is equal to what? This one move there. What about M1, U1 plus what? M2, U2. So this is what? The law of conservation of momentum. They are saying what? The total momentum, this one is what? Before and after. We are going to talk about collision in the next class, the next video. That's where we want to emphasize on collision. Now, he says that what? The law of conservation of momentum says that the total momentum, the sum of what? The momentum before collision is equal to what? Total momentum after collision, provided what? No external force is applied to the system. provided the system is what? In a closed or isolated system. The total momentum before collision is equal to total momentum after collision. It means that momentum is what? Is conserved. It means that the momentum of what? Or change in momentum of one is cancelled by the other. That's what they mean. The change in momentum of one body is cancelled by the other body. Now, since we know that now, this is what? We are coming back to this to explain a lot about this. But before we go back, now there's something I want to explain there that I needed to know. It is possible for this is a single body. It is possible for a single body to have three things. Number one, it can be like this. When will it be minus like this? When there is a braking force applied. It can be minus like when a braking force. So the net force applied is a braking force, braking net force. So you have that word, that particular word, formula. So if a braking force is applied to it, you will have that formula. Now let us see a case where rebounds. That is rebouncing. Now let's say a ball is coming of mass m, hits this particular wall, and it rebounds. It rebounds rather with u what? 1. It what? Hits the wall with what? The wall with what? V1 and rebounds with what? U1. What will be the force? The net force on the wall. The net force will now be what? M1 V1 minus what? M1 U1 over time. That will not be my what? My rebound velocity. This is what? Rebound what? Rebound force. So the force that the body will use to rebound. So minus and minus is what? Plus. So if you calculate it very well, you notice that what? You will now have the formula to be what? F is equal to what? M1 plus M1 times V1 plus M1 U1. That means F is equal to what? M1 V1 plus what? M1 U1 for rebounding is C over T, because when it rebounds with what? A negative what? Velocity in the opposite what? Direction. So in that case, it will not be plus. Take note of this. This one is for what? For braking force. This one is for what? For rebounding of a single object. So please take note of that. When the body rebounds, that is what will happen. Now let's go back to what? To this what? Force. Now, I was telling you something about the change conservation of momentum before we switch to explain this one briefly. We are coming back now to it now. I said the total momentum before collision by two objects is equal to total momentum after collision. That means that if I have what? M1 moving with velocity U1 and M2 with velocity U2. After collision, this M2 one move with velocity V1 and M2 move with velocity V2. Now what we are saying now is that the total momentum before collision, this is what? Before what? And this is after. Before collision is M1 U1 plus what? M2 U2. And after collision is M1 V1 plus what? M2 V2, which I have proved with what? Newton's third law. So that means that basically the foundation upon which the law of conservation of what momentum is defined is based on Newton's third law. That states that for every action there is equal and opposite reaction. Now let us go to the application of what? Law of conservation of what? Of momentum. And what I will be taking first, I will be taking what they call bullet and gun application. Now, bullet and gun application. I want to do the application of what? This law quickly. Let us look at it and let us what? Take it, digest it. We want to look at the what? The application of what? This Newton third law of motion. We want to look at the application. Number one is what? Let's have the gun like this now. This is a gun. We fired. Now, if this is a gun now, before we want to look at it, it has a mass of gun and the velocity should be acting this way after being fired. Now, before they fire the gun for release bullet, what happens is that the change in momentum is equal to 0 because the body is at rest. The body has not what? The gun has not what? Has not been fired. So in that case, the momentum is what? Is equal to the change momentum equal to 0. Let's say equal to what? Let's say after being fired, what happened? We notice that what? The bullet went out. Now this bullet has a mass mb with a velocity ub, velocity of the bullet, or let's say depending on what let's use vb, because after collision, after being fired, that's what happened. Then the velocity of what? There will be a recoil velocity of the gun in this direction. Then the mass of the what? Of the gun will be this. So the momentum will now be mass of gun times velocity of the gun plus mass of bullet times velocity of the bullet. Now, if you now equate the two of them now, Now, if you equate the two of them, this is what we want to have. Then let us make mass of velocity of gun the subject of formula. I want to have what? Minus mb vb is equal to what? mg vg. So divide both sides by mass of the gun. What we want to have is what? This will cancel. So velocity of the gun is equal to what? Minus mb, mass of bullet, velocity of bullet over mass of gun. Now, why is this minus? This is what we call the recoil what? Velocity of gun. Velocity of what? Of gun. So this is the recoil velocity of the gun, which will move like this. So why a minus sign? The minus sign is what? Due to what? The negative sign is what? Due to opposite what? Direction. Opposite what? Direction of the what? Of the velocity. So please take note of that. Very important, you know that. Opposite direction of the velocity. That is why the minus is indicated. Now we are done with this one now. Now the next one is what? You can also use this one for refill. So we are saying question, we can use it for refill. You understand now? Then, but let us look at what? Another second application, which is what? Rocket propulsion, or what we call the jet propulsion anyway. Now, what will happen here in the rocket propulsion? Now, we notice that something will happen now. Because if I have a rocket here, and there will be a what? The exhaust will go there. Now, initially, the mass, before collision, the mass of the what? Of the rocket times what? Velocity of the rocket. And before collision, before what? Before momentum before. What about the momentum after? Momentum after, it will have, by that time, there will be a change in mass. So which is what? M minus what? The change in mass when it is moving. Because that means that there will be, if you assume the fuel now will be reduced for the rocket, the fuel will be reduced and the total mass will have been dropped. But the velocity will increase. V plus what? Change in V will increase. Not only that, again, that will occur. Now, also, there will also be what? The change in mass that will occur as a result of what? The exhaust. This exhaust have what? A change in velocity, which is this. The velocity of the jet initially minus the exhaust velocity will give us what? This what? The velocity that this will produce. So the mass of the what? Of the rocket will have changed thereafter. After the velocity have increased, there will be what? The increase in velocity by this factor. So now, if we open up the bracket, now we would have mv is equal to what? Mv, this one multiplied by this, then times what? This one now be plus m change in v, then this one will give us what? Minus change in mass times v, plus what? This one now times this will give us what? Minus change in mass times what? Change in velocity. Then what will happen now for this one was plus what? V change in mass minus change in mass plus times what? This times this now is this one. This times this is what? Times exhaust velocity. Now what I want to do now is that this is before mv and this after. That's why there is a reduction in mass and there is an increase in velocity. Then for the exhaust produces a change in mass and a difference in velocity, which is the velocity possessed initially minus exhaust velocity. Now in this case now, change in mass and change in velocity is just too small. So you remove it if you cancel. So if you cancel this one out, then this one on the left hand side will cancel this one on the right hand side. Then change in mass times v, we cancel change in mass. This is also what? Change in mass times v. They will cancel out, minus plus cancel out. So what we have left will now be what? M what? Change in velocity minus change in mass what? Times exhaust velocity is equal to 0, which can be written as what? M dv minus what? dm ve dm is equal to 0. Now, having gotten that, now what we're going to do is to take this one to the other side. We have m dv equal to what? V exhaust velocity times the mass exhaust velocity, which is the exhaust, because there will be a reduction in the speed in this manner. That's why it's v minus what? But there will be increase in the forward what? Velocity, which is this one, and there will be reduction in mass. Now, since there is a reduction in mass, this one will carry minus. So this one, the dm, the change in mass, will carry what? There will be lost in mass. There will be final will be smaller than initial. So because of the fuel will have been gone, then the total mass will have what? Initially will be higher than the mass after. So this is what we're going to have. Now the minus we see remain even when you are taken to the other side. Now because of the mass, if you integrate now, this will take what? Divide both side by m. Now you might not be concerned, some of us might not be concerned with this, but if you integrate this one now, it will give you what? Ln what? Now taking what? M final minus m initial. Then this one now, take this one as what? V final, then V initial. Then V final, V initial, uppercase V final, lowercase V initial. Integrate in velocity. So if you do that quickly, if you do that, let me in this side. If you do that quickly, what you are going to have is that you are going to have it as what? The V integral of V final, V initial is equal to what? Exhaust velocity. Then dm over n. If you integrate now. Now, if you integrate this one now with respect to m, I want to have what? This is what? M final and m initial. You are going to have what? As what? Minus exhaust velocity ln what? M, the upper is what? M final minus M initial. Upper and lower. Upper and lower. So it's equals to this one. If you integrate, you are going to have V, then you are going to have what? V final, V initial. So if you put it there using using integration, you are going to have what? V final minus V initial equal to what? If you put the upper minus lower, I would have a minus V ln the final, the upper, minus what? Ln M initial, lower limit. Now, if you have gotten that now, what we are going to do now is to what? Is to change this one. Don't forget ln A minus ln B is equal to ln A divided by B. So in that case, you are going to have what? Minus exhaust velocity equal to ln M final over what? M initial is equal to what? This is what we call the burn out velocity. Burn out velocity. So V final minus V initial. So this one is burn out what? Velocity of the rocket is equal to what? Exhaust velocity, because V final minus V initial is burn out velocity. Ln what? M final. M final is what? Mass of total minus mass of fuel. Please take note of that. This mass of fuel divided by what? Mass of total, because initial mass is total mass. Now, before you start, the jet or the rocket, the total mass, the mass of the total mass, the mass of fuel plus mass of rocket. But after you have worked, just like a car that you filled up, you are going to work, you are traveling. After getting to a various destination, you notice that the fuel will have been reduced. That means the mass of the fuel initially plus the mass of the car equal to total mass. But after moving from point A to point B, the fuel mass will have reduced. Therefore, it will now be what? The mass of the fuel removed from total mass. So the M final is what? Mass of what? The rocket and the fuel, which is mass of total, minus mass of fuel over mass of rocket and the what? And the fuel. So this is the formula. So we can write it, just circle it. You might not take all other things, but take this one. Mass of total mass equal to mass of fuel over mass of what? Total mass. So this is what? The formula to use for rocket. The last one is what? The last one, I need to check my mic. Angle is working. The last one is the what? Shuttlecraft. The shuttlecraft. Now, I will start on where I stop from here. We have what? M dv is equal to minus exhaust velocity dm. Now, if you divide this, what we stop. If you divide both sides by the t, I would have the t over the t, which is this one now become force or thrust of the shot. I'm talking about shuttlecraft now. Now, this mdv is like mass times what? Acceleration is equal to minus what? Exhaust velocity over m over t. So this one is like rate of what? I got it from here by dividing this equation by the t. So the mass over t, m over t is what we call the rate of mass. Rate of mass. Then times what? The exhaust velocity. Then divide both sides by what? By mass. I'm going to have mass here. Now remain acceleration here. This is A is called the initial acceleration of the shuttlecraft. Initial. What about the M? M is what we call the total mass. Total mass, which is equal to mass of what? Of fuel plus what? Mass of what? Of shuttlecraft. So this is total mass. just like mass, this one I will take total mass now, m total. So let me call it m total. So total mass is it here. So this is what we call initial acceleration. Don't forget I told you this is F is thrust. So thrust is everything here now. Is equal to what? This is what? MA, which is MA, is equal to what? Exhaust velocity times what? Times rate of mass. But better still, what I will advise us to do is that this is thrust, which is equal to mass, total mass times what? Acceleration. Total mass times acceleration. So we can get the thrust by using what? Total mass is mass of web plus mass of what? Shuttle. Then multiply by the initial acceleration. We get the thrust. So the thrust now is what? The mass of the fuel. Then I'm just using some acceleration plus mass of the shuttle. Before, it's just like before you start the car, there's a mass of the car and the mass of the fuel. When you now move from to cover some destination, to cover some distance, a reasonable distance, you now notice that the fuel will have dropped. So in that case now, we are not talking about a case where the fuel dropped now. We are talking about the mass of the fuel plus mass of the car. That is just the same thing I'm trying to do. That is the acceleration equal to the thrust of the shuttlecraft. So this one will help us to what? To understand some things about what? About what we call law of conservation of momentum. Now let me drop the last thing there. What do you need to understand about what law of conservation of momentum? Law of conservation of momentum now, take note. It is applied to the what? The entire system, but not applied to individual object. It is applied to the entire system, but not applied to individual object. So if you talk about, we say the total mass, total momentum before collision, total, both the two bodies we combine together. Total momentum before collision is equal to total momentum after collision. We are going to look at collision in the next part B of this particular video. Now, what about the internal forces? Now, internal forces do not violate the law of conservation of momentum. Why? Because internal forces produce equal and opposite what? Magnitude of force. You understand? So they keep the momentum constant, or they conserve the momentum. So internal forces does not violate the law of what? Conservation of momentum, because they produce equal and opposite what? Forces, internal forces within the system, equal and opposite forces within the system. So they conserve the system. Number 3 is that the momentum of one is cancelled by the other. You understand? You must note this. The momentum of the first body, is cancelled by the what? The momentum of the other bodies. That makes it a what? That makes the what? The what do you call it? The momentum to be conserved. So take note of this. Now they ask a question. I want to know whether you'll be able to what? Get it. They said, let me read the question. It said, which of these following is not applicable to what? To Newton's third law of motion. Which of these following is not correct, rather, to about what? Newton's third law of motion. I say law of conservation of momentum. Which of the following is not correct about the law of conservation of momentum? A says what? Newton's third law is applicable to the law of conservation of momentum. That's option A. B says what? Let's look at B. B says what? The internal forces do not violate the conservation of what? Conservation of linear momentum, since there comes in equal and opposite pair within the system. C says what? The momentum produced by one is cancelled by the what? Opposite what? Momentum. By the opposite what? Momentum produced by the other. Yes. Then the last one says what? The what? Momentum is what? Law of conservation of momentum is applicable to individual object, but not apply to the total momentum of the system. Wrong. So the first one is correct. That says that the Newton's third law is applicable to law of conservation of momentum. Number two is also correct. That says that the internal forces do not violate the law of conservation of momentum because they produce what equal and opposite what pair within the system. The last one, the C, says what the momentum of one is what produced by one is cancelled by the other. So it is what correct. But that last one, that momentum, one of momentum is applied to individual object, but not the total, what not the entire system. No, it's wrong. So the answer is what? Which of them is not correct? Is that D is not correct, but A to C is correct. So see you in my next video. I believe you have enjoyed this class, because in the next video we're going to talk about collision of objects, and we're going to be looking at different collisions in terms of elastic collision and inelastic collision, and how they can apply. How can we conserve their momentum? We are going to bring in momentum, law of conservation of momentum, into the application of collision. Then we are going to look at the law of what? Law of what? Conservation of energy. How does it apply to elastic and inelastic collision? We look at the coefficient of restitution of an elastic body. Those are the things we are going to look at in our next video. Stay what? Safe and enjoy yourself. Make sure you are subscribed if you enjoyed this video, and ensure you click the notification button to always get more of our video. If you are a new subscriber, thank you for subscribing, and if you are a returning viewer, thank you for watching. God bless you. Enjoy your day.